SQL Map. Let's use SQL Map on our sample web application. We could use SQL Map as a fully automated tool to crawl a site, but as penetration testers, it is often more useful to manually explore a target before running another automated tool against it. While we could use any of the pages in our SQL Sandbox application, we'll focus on SQL Sandbox SQL Map. With Burp Suite running, let's visit the page with the embedded Chromium browser. We'll click Submit Query to load some results in the page. Let's switch to Burp Suite and review the requests and responses. Since the response from SQL Map API seems to include data from a database, we'll provide the request to SQL Map as our starting point. Let's run SQL Map. We will set the URL we want to scan with -u. We'll set method post to send a post request. Then use data for the post body, and specify the parameters to test with -p followed by a comma-separated list. We will exclude the DB parameter since the application uses it to determine which database to use. We will also update the post body to make sure the name parameter isn't empty. SQL Map will issue multiple requests to determine a parameter's vulnerability to SQL injection. It also attempts to determine what database software is being used so it can adjust the attacks to that software. As it is running, it may prompt us for the test to perform. In this case, we can accept the defaults by pressing Enter when prompted. However, by reducing the number of requests, the scan might fail to identify some vulnerable parameters. With any automated tool, we need to balance the speed and coverage of a scan. Once SQL Map has identified a vulnerable parameter, it will ask us if we want to keep testing the other parameters. For the sake of demonstration, we will accept the default, which is to skip the other parameters. After several moments, SQL Map will complete its scan and present the results. In this case, it found one vulnerable parameter and used two different techniques to exploit the vulnerability, listing a payload for each technique. Even when SQL Map is doing the work for us, having these sample payloads helps us understand how it exploited the vulnerability. We can now use SQL Map to automate the extraction of data from the database. We will run SQL Map again with dbms to set MySQL as the backend type, and will dump the contents of all tables in the database. The data extraction's duration will depend on which injection techniques can be used. According to the output, SQL Map was able to dump the contents of the entire database. In addition to displaying the contents in the terminal window, SQL Map also created a CSV file with the dumped content. SQL Map has many other features, such as the ability to attempt web application firewall bypasses and execute complex queries to automate the complete takeover of a server. For example, using the OS shell parameter will attempt to automatically upload and execute a remote command shell on the target system. However, this feature only works if the database writes to the application's web root and the application is written in ASP, ASPX, JSP, or PHP. When it does work, this shell can be somewhat slow, but it can provide an effective foothold to gain access to the underlying server. SQL Map stores information in a session file to speed up tests against URLs that it has already scanned. In the case of our sandbox application, this can be detrimental since we can select which database the application uses. We can instruct SQL Map to ignore any previous sessions with the flush session flag. As with any automated tool, SQL Map can miss SQL injection vulnerabilities. It may incorrectly identify the database, skip relevant test cases, fail because of arguments we apply, or fail because of misconfigurations on our part. Also, we should not rely on a tool if we do not understand how the tool works. However, we should consider using it in conjunction with tools like Burp Suite and Wireshark to capture what the tool is doing, and then attempt to replicate the attacks manually. This is often a very effective learning technique and should not be overlooked. Discovering the vulnerable parameter. Let's start by navigating to the page and logging in. After authenticating, we'll click on Admin in the upper right-hand corner of the page. At this point in a web application assessment, we would enumerate the application by completing a walkthrough in our browser consisting of clicking through the menu options to search for interesting functionality, and then inspecting the requests and responses in Burp Suite. For this case study, we'll find something interesting by clicking on Users and then Manage. When we check our HTTP history in Burp Suite, we will find that this page was loaded after a post request that included many parameters in the post body. There are a lot of URL encoded fields in the post body. Let's use Decoder to decode them. We will select the post body by clicking at the start of the body, dragging our cursor to the end, and then right-clicking and selecting Send to Decoder. Next, we'll click on Decoder. We can decode the text by clicking on Decode As and selecting URL. The decoded text will appear in a new text box. As the decoded text is one long line, it can still be difficult to read. We have added line breaks in the following excerpt. Most of the field names sound interesting. Words like columns and search are enticing when we're searching for database-related functionality. If we want to test for potential SQL injection vulnerabilities, we could try adding a single quote to each value. But first, let's examine the values closer. 3 parameters near the end of the post body are very interesting. A SQL query could use the value ascending in an order by clause or use the start and length values to limit results. Let's use Repeater to manually test these 3 fields. We'll return to the HTTP History tab by clicking on Proxy, then HTTP History. We can then right-click on the post body and select Send to Repeater from the context menu. Next, let's click on Repeater. It is usually a good idea to have a baseline request and response to refer back to, so we'll click Send before making any modifications. Once we have the baseline response, we can start making changes to the request. We'll add a single quote to the order, start, and length values. However, without knowing the structure of the SQL query, we need to be careful using single quotes to test multiple fields for SQL injection, so we don't accidentally create multiple closed strings, resulting in a technically valid query. Our goal is to cause an error in a SQL query by introducing an unbalanced or non-closed string. If the application uses the start and length values to limit the results of a SQL query, the values are unlikely to be quoted in a query since they need to be numeric values. Likewise, the keywords for sorting results in a SQL query are not quoted. We can reasonably assume that injecting 3 single quotes will still cause an error if all 3 parameters are vulnerable. The first 2 single quotes will essentially cancel each other out by creating an enclosed string, leaving the third quote to start a new string that will hopefully be unbalanced and cause an error. Let's send the modified request to the application by clicking Send in Repeater. We receive an interesting response. It seems the application has some input validation based on the error message. Since the message doesn't mention ASC, we'll leave the single quote there. Let's remove the single quote from the start value and resend the request. We receive the same error stating the length parameter is not valid. Let's remove the single quote from the length parameter. At this point, we only have a single quote in the order parameter. Let's send the request again. The server still responds with an error message, but this time it includes the SQL statement that caused the error. This message confirms we are injecting into the order by clause. This means we won't be able to use a union-based payload, but we should be able to use an error-based payload. The error message also reveals the database is MySQL. Since the database is MySQL and the application returns verbose error messages, let's try using an error-based payload with the extract value function. Our first attempt will be to extract the database version. We'll need to URL encode any spaces in our SQL payload by replacing them with plus signs, update the vulnerable parameter, and click Send. Excellent. The server response includes the database version number. We have confirmed this parameter is vulnerable to SQL injection. Before continuing to the next section, make sure to follow the steps above and confirm the SQL injection vulnerability. Exploiting error-based SQL injection. We have successfully identified that the order parameter is vulnerable to SQL injection. Our next step is to work on data exfiltration. We know error-based payloads work, so let's try using one to get the database names. Since the extract value function can only handle subqueries that return a single value, we'll have to get creative with our payload. MySQL has many functions we can use to aggregate data values. The group concat function concatenates multiple values and returns a single string. This function will work perfectly with extract value, which needs a single value. Let's use the group concat function to extract the schema names from information schema tables using the following payload, which includes line numbers and formatting for readability. Let's start with the innermost subquery on lines 4 through 6. This subquery selects the table schema column from information schema tables and groups the results, returning each unique value only once. Lines 2 through 7 use the innermost query as a table, using the group concat function to aggregate the results into a single record. When we use a subquery in place of a table, MySQL requires an alias to use as a table name. Lines 1 and 9 take the result from the group concat subquery, concatenate it with a greater than symbol, and pass the resulting value to the extract value function. Let's add our payload in repeater. We'll need to URL encode the spaces. Next, we'll click Send. As expected, the server responds with an error. The error message includes the list of database schemas. The value PWGO matches the name of the application and likely contains the application-specific tables. Now that we know the name of the schema used by the application, we can update our payload to extract table names. We'll need to instruct the subqueries to select the table name column from information schema tables and include a where clause in the innermost subquery to limit the results to the PWGO schema. However, when we submit this payload to the server, we encounter an issue with the response. While our payload worked, the output of the XPath error only displays 32 characters. This hinders our ability to extract information, but we can adapt our payload to iterate through the potential values. In fact, the query we are injecting into has an example of the limit syntax we want to copy. When used this way, the first number indicates how many records to skip, and the second number indicates how many to return. The example from this query will return the first 10 rows. We can also use the offset keyword to specify the starting offset value along with a limit. We'll use the following syntax and update our payload to iterate through the table names. Since we are limiting the potential output to 2 tables at a time, we will need to submit this payload multiple times. Let's update the offset value each time to iterate through all potential table names. Much like we did while enumerating the web application, we're searching for any tables that might contain interesting or sensitive data. Eventually, we will identify the PWGO users table with an offset of 32. The PeeWeeGo users table might contain passwords or other sensitive user information. Let's try to extract data from it. But first, we should query the database to learn what columns the table has. Before we change our payload, let's create a copy of it in Repeater by right-clicking on the request and selecting Send to Repeater. Once we've switched to the new tab, let's update our payload to select the Column Name column from the Columns table in the information schema. We'll remove the limit and offset values for now, as we can always add them back in. Let's paste our updated payload. When we submit the new payload to the application, we receive the following response. The response values are truncated, but we were able to identify a password column. Now that we know the column names, we can start extracting data from the PeeWeeGo users table. Let's try to extract passwords. We don't know how long the password field is, but the XPath syntax error limits output to 32 characters. We can use the substring function to work around this limit. This function takes 3 parameters: the column name, the starting point, and the length or number of characters to return. Since we're targeting a new table, let's create another copy in Repeater and switch to the new tab before modifying the payload. We can keep our requests organized in Repeater by using different tabs for each logical attack. Let's update our payload to select a 32-character substring from the password column. We'll place the updated payload in the order parameter on the new Repeater tab and URL encode the spaces. We will reintroduce a limit clause so we can control which row to extract, but we can remove the group concat function since we'll be extracting one record at a time. Let's submit the payload to the server by clicking Send. Our payload worked, and we have obtained part of a password value. The characters at the start of the password indicate this is a password hash. We'll need to update our query to extract the next 32 characters to get the full password hash. While we cannot use a password hash directly to further our access to this application, we have proven that we can use error-based SQL injection payloads to access any data in the database by working around character-based limits. Directory Traversal Overview. Rather than working from a web application, we can illustrate directory traversal straight from our attacking machine. We'll specifically take note of our present working directory in our Kali Linux VM. Let's perform a legitimate directory traversal. The command enables us to traverse outside of our home directory and read the contents of etc password by prefixing the location with 2 traversal strings. We were able to read the contents of the file by using traversal strings. Traversal strings are, in their simplest format, 2 dots followed by a slash. For example, ... means entity before this, whereas providing a pair of traversal strings means take me back 2 directories. Because we performed the command from our home directory, we traversed a total of 2 times back to the root file system location. For example, let's suppose that we use curl on the megacorp1 domain. We will provide curl with the -v argument to increase the verbosity of the output, followed by a specific URI, and append a single traversal string and index.html. Finally, we save the page contents to a file with the -o argument to clean up the output so we can examine the results of the get method. Our traversal string resulted in a GET request being made to index.html. Using curl ensures that the web browser is removed from the equation if traversal is being rerouted back to the web root. Absolute pathing. Let's execute a command with absolute pathing from our Kali Lab VM. We'll run cat and provide /etc/group as an argument. By specifying a / at the beginning of our statement, we tell Linux that we're interested in the etc directory from a file system perspective. The / directory is known as the root fs or root file system on Unix-based systems. This technique is known as absolute pathing since, depending on the operating system, we specify a path that includes a volume label, begins at the underlying root file system, and concludes some number of directories down the line with a file. In our example, we arrive at the group file within the etc directory. Relative pathing. When working with relative pathing, we can always expect to encounter a reference URI or directory. This reference URI can be any file path on the target web server. However, when specifying the path, rather than starting in the root file system directory and moving over to a particular file, our query is much shorter as we already exist within the relative directory. For now, let's examine the command from the etc directory on our Kali VM. With our relative pathing example, we access the group file inside the etc directory. The key difference in this case is that we did not instruct the Linux kernel to read /etc/group directly as an absolute path. Because both our relative directory and working directory are etc, we only needed to cat the group file. We've now demonstrated the difference between absolute and relative pathing. Let's now consider our Kali Lab virtual machine. Starting from our home directory, we can traverse outside of that relative directory to view a file or perform an action using the .. traversal string. Let's read the contents of etc group from within our home Kali directory. These concepts will be foundational to growing our directory traversal skills. Directory listing. Let's open our web browser and navigate to our target to examine the web application and parameters available to us. In this example, we will attempt to abuse improper input sanitization on a demo version of a PHP file browser. Our version currently only supports listing the directories and files present on the target web server. It quickly becomes clear that we only have a few directories to choose from. Let's select the CSS folder to begin understanding how this application works. It would seem that the web application is working fine and the end user can browse directories at their leisure. If we further inspect the URL address bar, we'll notice something that stands out and suggests we test the path parameter. We will examine this more closely in the next section. Parameter analysis. The value of the path parameter in the query string suggests that we might be dealing with absolute file pathing. Based on the path, we can assume that the underlying OS is Linux. In addition to learning that the target is most likely running Linux, the path parameter also suggests the existence of a web root. This might be the web root for the current application or another application, and we'll need to conduct a bit more testing to discover what exactly we've found. In the next section, we will discuss evidence of a directory listing finding. Evidence of directory listing. To confirm the presence of a directory listing, let's first replace the path value with %2f, which is the URL encoded equivalent of /. We can confirm that the path variable is indeed vulnerable to directory listing. We have traversed outside of the web application's working directory and back to the web root. Next, let's try to abuse this directory listing and inspect the var directory of the Linux root file system. With this particular application, we have two options for reaching our goal. We could, for example, specify traversal strings by appending 3 traversal strings to the path variable, instructing the path variable to move backwards from the web application's working directory 3 times. Let's take the other option and attempt to exploit this directory listing into the var directory by supplementing the value of the path parameter with var as an absolute path. We are now located in the var directory and have listed its contents by specifying an absolute path to the path parameter. Now that we've practiced directory listing and worked with the path parameter, let's attempt data exfiltration. In our attempt to retrieve the contents of etc password, we notice that we run into some challenges exploiting this directory listing finding. The error indicates that the target application does not permit us to read files from the operating system. However, it does allow us to list the files and directories. This information further confirms that we are dealing with a directory listing finding as opposed to a directory traversal. In a genuine directory traversal, we would have simply extracted the contents of etc password. We're not entirely out of luck, however. Although we are not able to display the contents of etc password, our file browsing permissions nevertheless enable us to attempt traversal into specific directories with the intent of finding a service running on the target machine. Although we cannot display its configuration data, we can gather more information to help us with further attacks on the target system. Let's attempt to probe into the home directory of the target system to gather system-level users. These users can be added to our enumeration data in our master note file for further attacks either on this machine or across the network at large. To begin our inspection, we'll modify the payload value. Wonderful, we have discovered a valid system-level user. It's important for us to keep in mind that the directory listing is only one of many findings we may encounter with traversal strings. We should always verify opportunities that might seem like a directory listing finding, but in reality could be much more useful. Directory traversal, exploitation. Let's switch to our directory traversal sandbox for this example. In this application, we'll find a few options to select from. Our sandbox is configured such that we can experiment with both absolute and relative directory traversal exploits, with options for absolute pathing, relative pathing with verbose error messages, and relative pathing with suppressed error messages. We'll explore the absolute pathing page first. Let's keep in mind that we should provide a path parameter. An absolute path starts from the root file system. Our target is a Unix-based system, and inside of the web root is a file called data.txt. To access this file, we'll provide its full path to the path parameter. We have exploited poor input sanitization to the path parameter to achieve directory traversal with absolute pathing and exfiltrated the information within data.txt. Next, let's exploit our directory traversal using a relative path. In this section of the app, the input for the path parameter has been intentionally poorly sanitized in an attempt to limit any exfiltrated data from the web root. We can attempt to bypass this by providing traversal strings and moving backwards until we reach the etc password file. At this point, we've exploited both relative and absolute directory traversals, even extracting values from the target operating system. Fuzzing the path parameter. Now that we have successfully exploited a relative directory traversal, let's attempt to confirm which files are present on the machine in an automated manner using wfuzz. Wfuzz can return a significant number of false positives, so let's start with a dry run to determine the average error rate before we enumerate our target machine. In this command, the -c parameter will instruct wfuzz to display color in our terminal output window. The -z parameter is our payload parameter, and we specify that our payloads for the fuzz keyword will come from our LFI word list. We can filter out the erroneous output by using the HH option to suppress the 404 message response size. In this case, the average failure response sizes are 81 and 125 characters, so we'll provide these values to our HH parameter next time we run it. After filtering out errors using this technique, only relevant results will be displayed in the terminal output window when we use the HC option in wfuzz. We can now observe several verified etc password files on the target machine since the erroneous output has been removed. Case Study: Home Assistant. We'll be targeting Home Assistant for this case study. In early 2021, this application was found vulnerable to a directory traversal attack because multiple integrations into Home Assistant enabled exfiltration of configuration files, potentially leading to account compromise. In the following sections, we'll discover and exploit this finding ourselves. Initial Application Assessment. We begin our assessment knowing that burp is automatically forwarding requests from the Home Assistant endpoint to the HTTP History tab after we disabled interception in the Proxy tab. We observe that Home Assistant presents a fairly standard login form. Let's return to our forwarded requests in Burp Suite and inspect them manually by clicking HTTP History. Scouring through the history of our initial landing on the home page, we'll notice a suggestive URI, Font Awesome. This directory seems suggestive for a few reasons. First, sorting by URL in ascending order. We take note of the predominant calls being made from Font Awesome to the front end of the web application. These calls seem to be targeted at the static and front-end latest endpoints. Because we have enumerated the font awesome URI with Burp Suite's HTTP history, we can perform fuzzing with a common word list present on Kali Linux to check for different 404 response sizes. We've confirmed that font awesome exists from our Burp's HTTP history. However, if we encounter different 404 response sizes during our fuzzing attempts, we may be onto something interesting. Although this might seem like a lot of effort, let's stick with it. We will fuzz the web root using a common word list and only analyze the 404 response size. We'll note that for the purposes of this case study, a 404 response size in the web root yields 14 characters. Since we know the font awesome URI exists, we can also perform fuzzing on the font awesome directory to verify whether any third-party resources are being used with different 404 response sizes. A difference in 404 response sizes might indicate that another web application is generating a different 404 page than the web server software. Analyzing the difference between fuzzing the web root and the font awesome URI, we'll notice a total difference of 14 characters between the 404 response sizes. Because we now have evidence of two separate 404 responses, we can safely assume that whatever is handling those response sizes is out of the ordinary and might even indicate use of a third-party resource. With our enumeration complete and pointing towards font awesome as the vulnerable parameter, we are ready to begin the exploitation phase. Exploitation. To confirm directory traversal, let's attempt to manually alter any content after the font awesome parameter. We'll need to leverage many traversal strings to achieve our goal and reach the etc password file on the target operating system. Let's right-click the original request from our HTTP history in Burp Suite and select Send to Repeater. We'll replace anything past font awesome with several traversal strings directed towards the etc password file. It quickly becomes clear that our suspicions were correct about weak sanitization, and the font awesome endpoint is vulnerable to directory traversal. Now that we can expose the contents of any file on the target, let's scour the machine for configuration files that we might leverage to perform further attacks. After a bit of searching for Home Assistant configuration documentation on the internet, we find something particularly useful. According to the documentation, there is a configuration file we can use to probe the target machine. Now that we have reason to believe there is a file on the target machine pertaining to the underlying web application configuration, let's attempt to discover this file and extract its contents. We will move one directory at a time until we arrive at the configuration file. After 3 such traversals, we reach our intended location and the file is displayed. We have successfully located the configuration file and can safely assume that we are in a configuration directory. We can exploit this further by enumerating the entire OS. We'll use a word list in conjunction with a vulnerable endpoint to determine exactly which files are present on the target machine. Let's consider the output of the command, which fuzzes the font awesome URI. Great. The output confirms we've exposed the target operating system's configuration. This data can be extremely helpful for discovering new vulnerabilities and understanding future exploits. Case study: Apache OFBiz XXE vulnerability. In this case study, we'll examine an XXE vulnerability in Apache OFBiz, an open-source enterprise resource planning application. While XXE injection vulnerabilities can occur anywhere an application interacts with XML input, the vulnerability we'll be reviewing is found in the authenticated section of the application. For this reason, we'll be attacking OFBiz as an authenticated user. Discovery. We will start by opening Burp Suite and its embedded browser. Next, we'll access the login page and log in with the provided credentials. While exploring the application as an admin user, we notice the Web Tools page. After loading the page, we find that it contains several XML references. Since XML serves as an intermediary between human data and application objects, imports and exports are good targets to test for XXE, since they often parse XML. There are several ways we can import or export XML. Let's start by trying to export an entity so we have valid XML as our baseline. Ideally, we're searching for an object or entity that is displayed in the application and has a variable or attribute that can handle large strings of data. We'll begin by clicking on XML Data Export. But we find that the Out to Browser option does not work. When we attempt to use the feature, we receive an error. When we click on Programmable Export, we find another page that we can use to export sample products. The pre-populated XML at the bottom of the page lists multiple products. Let's examine the structure of one product. The long description field is a good target for our attempted XXE attack. The application should display that field and can likely handle arbitrary text. However, the XML specification does not allow external entities in attribute values. We will need to restructure the XML to use the long description as an element instead of an attribute. The application should still parse the XML as there are no hard rules in the XML specification about when to use elements or attributes. We will also update the product ID to make it easier to search for. Now that we have a baseline object, let's determine if the application's XML parser will parse an entity. We'll focus on the XML data import page, which we navigate to by clicking the XML data import button. Let's try a simple internal entity to determine if the application is vulnerable to XXE. The DTD definition is included at the start of the XML data. We will need to update the value of the long description element to reference the internal entity. We will enter our payload into the Complete XML Document text field. And then click Import Text to submit it to the application. We didn't receive any error messages, so we can assume our XML payload was processed. Perhaps we can find a page that will let us search for products. Let's right-click on Catalog and open the link in a new tab. Switching over to the new tab, we'll click on Products. We can enter our product ID on this page to search for the data we submitted and then click Find. There is one result. It seems the application did process our XML successfully. Unfortunately, this page does not include the long description field. Let's click on the product ID and then click on Content. We may need to scroll down to find the long description value. The application processed our payload and updated the long description field to the value of our internal entity. Now that we know that the application is vulnerable, we will revise our payload to extract data from a file on the server. Exploitation. Let's change our payload to an external entity and attempt to access etc password. We'll switch our browser tab back to the XML data import page and update our XML payload to use a new external entity. Let's click Import Text to submit this payload. After the page refreshes, we'll switch tabs and refresh the product details page. Excellent! Our XXE attack was successful and the long description field now contains the contents of etc password. We were able to use the XXE vulnerability to access files from the server. Note that the user profile running the application will generally dictate which files we can access on the server. Error-based exploitation. In some scenarios, we may not be able to directly retrieve the results of our XXE attack. To simulate this, let's modify our attack to use an error-based payload. If the application returns verbose error messages, we want to generate an error that will include the sensitive data from our XXE exploit. One way to do this is to place the payload in a field that will cause a validation error. For example, the baseline product example includes several attributes containing timestamps. Assuming the application validates the XML values or uses them in a database, the application might throw an error if we include a value in one of those elements that cannot be parsed as a timestamp. We've updated our exploit payload, moving the created stamp from an attribute to an element and placing our entity reference there. We also removed the entity reference from the long description element. When we submit this updated payload to the application, we receive an error. The error message reveals that the application is written in Java, but it does not contain our payload. If the XML parser does not return an error with our payload, perhaps we can target the database by placing our payload in a different field. Instead of causing an error based on data type, let's try to cause an error based on field length. We removed description as an attribute and replaced it as an element with our external entity reference as its value. We also need to update created stamp with a valid timestamp. Let's submit the new payload. We receive another error message, but this time it includes the contents of Etsy password. Upon closer inspection of the error message in Burp Suite, we find a key component of the error message. Based on the error message and our payload, the application likely tried to insert a string that was too large for the corresponding column in the database. If the contents of the file were short enough to fit in the column, we wouldn't have received this error message, and we would need to find another way to generate an error. Out-of-band exploitation. In situations where we cannot access the results of our XXC attack or obtain verbose error messages, we can attempt an out-of-band XXC attack. External entities can reference resources on other servers. An out-of-band attack leverages this functionality to exfiltrate data as part of the request that loads the external resource. For this attack to work, we'll need to create and host our own DTD file that contains two entities. We'll need to use parameter entities because we need the entities to be processed within the DTD so they can impact each other. Let's create a file named external.dtd. The content entity defines which file we are targeting. The external parameter defines another entity named exfil, which appends the content entity to a URL. We'll place this in our web root and start our Apache server. We'll also need to update our payload to use these entities. Since we're using parameter entities, we'll need to reference them within the doc type definition. We start by including a parameter entity that references external.dtd on our Kali host. Next, we'll reference the base entity, which will cause the parser to load the DTD file from our server and parse it. We will then reference the external entity, which is defined in our remote DTD file. The XML parser will expand the external entity, creating the exfil entity. Finally, we reference the new exfil entity, which will cause the parser to attempt to load a resource from our server with the contents of the content entity in the query string. Unfortunately, when we submit this XML payload, we receive an error from the server. The application encountered an error while parsing our XML data, but the important part of the error message is illegal character in URL. We attempted to append the contents of Etsy password to a URL. Perhaps there are characters, such as line breaks, within the file that are breaking the URL. We can verify the application requested external.dtd by checking the Apache log file. Let's update external.dtd to target a file that is likely one line containing fewer special characters. We will target Etsy time zone. Let's submit our payload again. We can ignore the error message that pops up. Instead, we'll check our Apache log file. Once again, the web application requested external.dtd from our Kali host and then made a request for out with the contents of Etsy time zone in the query string. While there may be some limits on what data we can access using an out-of-band attack, this is still a very useful technique against a vulnerable parser when other XXZ attacks fail. Twig Discovery. Twig is a popular templating engine for PHP. Prior to Twig's rise, PHP developers would often write inline PHP within documents. This early development style left a lot to be desired. Developers often left security gaps, which could lead to attacks like XSS using inline PHP. While these types of applications still exist, with the rise of PHP frameworks like Laravel, Symfony, Cake PHP, and others, inline PHP applications are slowly going away. These type of frameworks commonly expect developers to use a Model View Controller, or MVC, design pattern, or something similar. This type of design pattern pushes for separation of how the data is processed and displayed. Because of this separation, templating engines like Twig are very popular. In fact, Twig is developed and maintained by the Symfony framework, but it is supported by almost all other frameworks. Now that we've covered MVC fundamentals and a bit of Twig's history, let's review the syntax of a rudimentary Twig template. We can find an example in the sandbox by visiting the Twig route on the template sandbox. Within this template, we can find examples of a statement, expression, and static content. Let's first review the if statement at the beginning. This statement will first check whether the admin variable is true. If the user is not an admin, the output will include sudo. If the user is an admin, then sudo is not necessary. We can check the value of admin by reviewing the variables. In PHP, a value of 0 can be treated as a Boolean value of false. Next, let's review the statement that prints the name. The name variable is pushed through the capitalize filter. This is one of the many filters Twig offers by default in all templates. Filters like these are what make Twig more logical than logicless. However, we must remember that more logical templating engines are more likely to expose security gaps. We will review how to exploit this later. Reviewing the variables, we should be able to determine what the name variable is set to. We'll notice the name edvines is output in this location. Twig syntax is very similar to many other common templating engines. However, when we are attempting to inject into a template, it's essential that we know what templating engine the target is running so we can use the correct syntax. As we become more familiar with various templating engines, this concept will make more sense. While it might seem that curly brackets could be a giveaway that the target templating engine is Twig, other templating engines might share the same delimiters. In addition, most templating engines allow developers to change the default delimiters, so we can't always base our decision off the delimiters alone. With that in mind, let's attempt to find other indicators that the templating engine might be Twig. For example, we could compare how arithmetic is performed when two integers are provided versus when a string and an integer are provided. Let's first review the output when we multiply 5 by 5. We'll do this by creating a new statement and using the asterisk character to multiply the numbers. In the template sandbox, we can edit the template by replacing the text in the upper left pane of the page. The output here is 25, as expected. Now let's change one of the numbers to 5 in quotes instead. The output again is 25. This is because PHP does not check the type of the variable and will automatically treat 5 with quotes like the number 5. We can leverage this to help us discover what templating engine is in use, since not all languages behave the same way. Later in this topic, we'll work with this output using a language that is more stringent about variable types. Another way to determine if the target is using Twig is by reading the documentation and finding unique pieces of syntax. For example, Twig supports adding a dash character to the delimiter to trim white space. This means if we add a couple of extra spaces, use a statement with a dash character, and review the output, we should find that the output won't have the extra white spaces if the target is indeed running Twig. The documentation for templating engines is extremely useful in SSTI exploitation. Twig exploitation. While Twig does not advertise direct access to its underlying language, PHP, it does provide several filters that might be useful for us. We'll start our review by checking if any of the filter names stand out in the documentation. Typically, filters like currency symbol and inline CSS don't stand out since these usually don't need to execute any function to receive a response. They may simply manipulate an integer or review a string. We're unlikely to find an execution path in these filters. We want to review filters that have closer ties to the programming language and might accept functions to process data. For example, filters like filter, join, map, reduce, slice, and sort stand out since they might accept functions for additional processing. Let's open the documentation for Reduce and read how this filter works. The documentation states, the reduce filter iteratively reduces a sequence or a mapping to a single value using an arrow function to reduce it to a single value. We'll also find a documented example. The most important thing for us to notice is that this filter accepts a function, an arrow function in this case, that is executed by the filter. Knowing exactly what arrow functions are and how they work is less important. If we can control which function to use, we might be able to execute arbitrary PHP functions. Reviewing the arguments, we can find some hints about how to achieve this. For now, we'll use var dump as the function and provide a random string as the argument. We also need to provide a value on the left side of the filter, so let's use an array with only a single value. If we place this in our sandbox, we'll receive a variable dump of the string. The var dump function was executed with the hello string as an argument. Let's replace this string with something that will execute system commands instead, such as the system function. When we render this payload, we receive a response indicating which user is running PHP. Excellent! We can now execute commands in the Twig templating engine. FreeMarker Discovery. While Apache FreeMarker is a general-purpose templating engine, it is commonly paired with Java applications. Similarly to what Twig did for inline PHP, FreeMarker did for Jakarta server pages, previously known as Java server pages or JSP. FreeMarker provides a better option for developers to separate the manipulation of data from its display. Let's review an example FreeMarker template. This template includes a name variable and a reasons array. Let's break down this template to review its various components, starting with the first line. This line begins with a greeting that demonstrates a FreeMarker expression, which FreeMarker calls an interpolation. The starting delimiter is a $sign and open curly bracket. The ending delimiter is a closed curly bracket. In between, we'll find the variable to be displayed. In this case, hello, Ophira. Next, let's review the if statement. The if statement starts with what FreeMarker refers to as an FTL tag. These are very similar to statements in other templating languages. The top tag indicates the start of the if statement, and the bottom tag indicates the end of the statement. The top tag contains the syntax to check if the name variable is set to hacker. This means that the content in this section will only be displayed if the name is hacker. We can change the name to hacker and find the additional content is rendered. The content in between the if statement is generated using a loop. A loop also begins with an FTL tag or statement. The code loops through the contents of the reasons list, extracting each value into the reason variable. The reason is displayed with the reason expression. Before the reason is displayed, the index is extracted and 1 is added to the variable so that the list can start with 1 instead of 0. Before 2016, FreeMarker required developers to specify if a variable needs to be HTML escaped. It's easy to overlook this setting when displaying variables. After 2016, FreeMarker implemented a system that would auto-escape variables if the content type was an HTML document. However, most other templating engines will always escape HTML content unless specified not to. This means that applications that use free marker templates are much more susceptible to XSS than other templating engines. We can observe this by wrapping the name with an HTML tag. We'll set the name to be Ophira with tags. This results in the name being italicized, confirming that the HTML was rendered. We can leverage this tactic to execute XSS against the target. Since Java uses strict variable types, we can typically discover if a target is rendering free marker templates by attempting to cause an error by mixing variable types. For example, if we were to try to multiply two numbers, we'd expect everything to work. However, if we change one number to a string, we should expect a syntax error. While this isn't the strongest indicator, if there is reason to believe that we are dealing with a Java app, we find this specific delimiter being used, and the application crashes when multiplying a string, we can guess that the target is running FreeMarker. FreeMarker exploitation. Let's start once again by reviewing the documentation for a hint that might lead to file execution. A good place to start is the FAQs page. One of the questions asks, can I allow users to upload templates and what are the security implications? What better teachers to show us how we might exploit a library than the developers themselves? The bullet point towards the bottom gives us a great clue. It seems that FreeMarker supports the ability to initiate new classes. However, as the documentation states, the class has to implement the template model class. We know that the application has FreeMarker installed, so let's use the Java API documentation to review which classes we have access to. Reviewing the list of all classes, we find one called Execute. Not only does this page show a warning that it will allow a user to execute arbitrary code, it also shows us that it implements the template model class. We now know how to instantiate a new class and which class to use. Let's put it together and build the payload. The payload will first reference the class we found that can execute arbitrary commands. Next, it will use the technique FreeMarker warned us about to create a new instance. Finally, it will run the whoami command using the response of the newly created class. Let's put this into our sandbox and review the output. In this scenario, the target is running the application as root. However, it is in a containerized environment, so this might not always be the case. Wonderful! We can now execute system-level commands in FreeMarker. Pug Discovery. Pug, previously known as Jade, is a JavaScript templating engine. While Pug is most commonly used for server-side templating, it also supports compiling templates for client-side rendering. Pug is commonly integrated with the Express framework in a Node.js application. The syntax for Pug templates is significantly different than the other templating engines we have reviewed so far. This is because Pug is specially designed to generate HTML files. Even its documentation for plain text discusses how to add plain text into an HTML document. Because of its design, Pug has syntax for specifying an HTML tag and tag attributes. Its method for defining a statement and expression is also different than other templating engines. Let's review a template and break down each section. This template is executed in conjunction with a couple of variables. The template begins with an expression to display an HTML h1 tag that greets the user with their name. The default delimiter in Pug is a number sign and an open curly bracket, with the closing delimiter being only a closed curly bracket. It's also interesting to us that Pug requires the first word to be the HTML tag that will wrap the following data. The content after the initial h1 will become wrapped in h1 tags. While h1 is a common HTML tag, custom values could be found here too. For example, if we started the line with foo, the contents after the first word would be wrapped in a tag named foo. HTML tags often require additional attributes. Pug allows us to pass attributes in parentheses after the tag declaration, as shown in the second line of the template. We'll observe that this HTML tag contains 3 attributes: type, name, and value. Since the type is hidden, this element won't display when the HTML is rendered. Following the input tag, we find an if statement. The showSecret variable is set to true in this template, meaning the first part of the if statement will be rendered. One interesting component of Pug is that keywords like if and else have specific meanings and are not treated as HTML tags. Instead, they are treated as statements. This is different than the other templating engines we have reviewed because there is no special delimiter that treats statements and expressions differently. Pug can also execute JavaScript code directly, a feature we'll find to be very useful later. We can observe this within the first line of the if statement. We are setting a secret variable to an array. Using the dash character in front of Pug indicates that the code should be executed by the JavaScript engine and the output should not be displayed. Pug also supports buffered code, which displays the output of the command. We can instruct Pug to run as buffered code by using an equal sign instead of the dash. Let's replace the dash with an equal sign in the template. We should observe the array displayed on the page. Finally, we find a loop in the Pug template that iterates through the secret array and displays each element on the page. As with the if statement, the each keyword has a special meaning and its contents will not be used to create an HTML tag. Instead, each value within the secret array will be shown in an HTML p tag. Now that we better understand how Pug works, let's think about how we could discover it on a target. Because Pug uses a format that's different from most popular templating engines, we can check the first word of a target template's new line to determine if it wraps its contents in HTML tags. If so, we're likely to be dealing with Pug. We'll use the payload 7x7 for a couple of reasons. First, if the output is 49, we'll know that we are most likely dealing with a language that is not strictly handling variables, like JavaScript or PHP. Next, since Pug expects the first word of a line to be a tag, it will enclose this with less than and greater than signs. Let's use this payload in the sandbox and review the output. The number 49 is displayed, indicating that this is most likely a Pug templating engine. Pug exploitation. The payload to execute code via Pug is, in some ways, more straightforward than others, since Pug allows for more direct access to the underlying JavaScript programming language. Because Pug is rendering on the server side, we know we're typically working with Node.js. Searching for Node.js execute system command, we'll find the documentation for the child process spawn sync command, which executes system commands on the target. Once the command executes, we can access standard out to read the output of the command. The child process module isn't accessible by default. Instead, we will need to use the require function to import it. Let's find out if we have access to the require function first. We'll use the buffered code feature of Pug to read the output of require if it exists. Unfortunately, the output was empty. This most likely means we don't have direct access to require. However, we can try to access require from the global object. While we don't need to develop a deep understanding of why this global object exists, we should know that in Node.js, global is similar to the browser's window object. If we indeed have access to the global object, we can access require by using global process main module require. This time, the source code of the require function is returned. We can create a new variable named require and set its value to the global process main module require function. We can now attempt to import child process again. We'll set the require variable in an unbuffered code statement since we don't need the output. We'll run the payload within the sandbox. While this output might not seem interesting, this confirms we have imported the child process object. All that's left to execute commands on the target is to run a command using spawn sync and access the output with standard out. Again, we'll run the payload in the sandbox. In this scenario, the target is running the application as root. However, it is in a containerized environment. This might not always be the case. Nice! We're able to inject into a Pug template to execute commands on the system. Jinja Discovery. Jinja is a popular templating engine for Python. We can find it in the sandbox by visiting the Jinja route. Unlike Pug, we'll find that Jinja's implementation is more similar to other templating engines. We'll start by reviewing the Jinja syntax, then discuss how we can identify Jinja templates. This template will be rendered with a name variable and an array of strings from the reasons variable. On the first line, we'll find an expression to display the name. On line 2, we observe an if statement with its ending tag on line 9. Lines 5 through 7 contain a for loop listing the reasons array. To find out whether a target is running Jinja, we can leverage the fact that Python handles variables differently than languages like PHP, Java, and JavaScript. For example, if we were to use 5 times 5 as a payload, we would expect 25 as the output. However, what would the output be if we were to use 5 times 5 with the second 5 wrapped in double quotes? Let's try it out. In this case, the engine didn't multiply the variables. Instead, it displayed 5 times. This is a great indicator that the target is running Jinja. Another indicator we can leverage is accessing global variables. These variables are often set by the framework in use. Jinja is developed by the same organization that developed the Flask framework, which is why they are usually paired together. Reviewing the documentation, we learn that Flask sets 6 global variables: config, request, session, G, URL for, and get flashed messages. Let's try to use request as the payload. Using this information, we now know that the application is running Jinja with the Flask framework. It's important to note that not all applications using Jinja will have these variables. It's also important to check if other frameworks set similar variables. Jinja exploitation. For Jinja, we'll take a bit of a different approach. While there is a payload that can be used to exploit and gain RCE with Jinja templates, it is much more complex than the other templating engines. For this reason, we won't investigate how to obtain RCE via Jinja. However, we can obtain other sensitive data. As we mentioned, each framework might set its own global variables. Some variables, like config, may contain application secrets like private keys or database passwords. Let's try to access the config variable using an expression in Jinja. We'll use config pprint as the payload. The config variable will be processed through the pprint filter to make the output easier for us to read. Our output displays the secret key, which may be used to decrypt sensitive data. Mustache and handlebars. Discovery. The Mustache templating engine is supported by multiple languages and frameworks. It was named Mustache for its use of the curly braces as delimiters, which look like a mustache when turned sideways. It can render templates on the server or client side using JavaScript. However, Mustache is unique compared to the other templating engines because it is considered logicless. While many other templating engines support closer access to the underlying programming languages via more complex statements and filters, Mustache only supports simple if statements to check whether variables exist or to loop through an array. Mustache is designed this way to help force developers to separate logic into the controller instead of the view. This inflexibility also provides some security advantages. Since we don't have access to the underlying programming language, it's much harder to exploit SSTI and achieve RCE. Instead, Mustache injections might only lead to sensitive information disclosure if we know which variables to display, or XSS. Developers often found Mustache too restrictive. Because of this, the Handlebars templating engine was created to offer more helpers and integration with the underlying programming language. The most popular Handlebars library is for JavaScript, which allows for client and server-side rendering. However, there are also Handlebars libraries for Java, .NET, PHP, and more. In this section, we'll focus on handlebars.js. Let's review a handlebars template to understand what it might consist of. We'll pair this template with a set of variables that define the name and nicknames. In this example, we can find the use of an expression on the first line displaying the username. We'll also notice a couple of default block helpers that act as if statements and for loops. While these are technically statements in a template, it's important for us to understand that these exist only because there are specific predefined helpers for if statements and each loops. Mustache and handlebars. Exploitation. Since handlebars is designed to be as logicless as possible, the attack surface for it is slightly different from the other templating engines we've discussed. Handlebars does not natively support functions that can lead to RCE without additional exploits. There have been exploits performed on handlebars reaching RCE using SSTI, but such exploits are typically patched. However, developers might add additional helpers to handlebars, thus exposing more of the underlying programming language to the template. To reduce time, developers might import pre-made helpers into handlebars. One example is a repository named Handlebars Helpers. Reviewing the Handlebars Helpers repository, we can find some helpers that might be useful to us, specifically read and read directory. The read helper is used to read a file from the file system. The read directory helper will return an array of files from the given directory. If an application uses the Handlebars templating engine and uses Handlebars helpers, we may be able to steal sensitive files from the file system. Since file system access isn't very useful on client-side rendering, we will need to target an instance to test this in which Handlebars renders server-side content. We'll use Handlebars Remote on the template sandbox for this. Let's start by using the read directory helper to list the contents of the Etsy folder. Since we know that this will return an array, we'll use an each helper to print each string in the array. In this list, we can find the Etsy password file. Let's use the read helper to display its contents. Great! We now have the ability to read a file on the file system and list directories. Using this information, we might be able to find a path to code execution.